It's a great pleasure today to have Chad All visiting us. Unfortunately, it's only a virtual visit, and maybe in the future we'll be able to visit in person. So Chad got his PhD, his Bachelor in Science in Physics from the University of Virginia in 2006. And after that, it took a couple of years of teaching to high school level students, and particularly spent 1 year teaching in Guatemala to high school level student. After that, he decided probably PhD was better than teaching to high school students. So he attended University of California at Berkeley, where he got his PhD in astrophysics in 2014. And during that period, he worked on developing a polarization system for a radio interferometer in California. And there where I actually met Chad for the first time. I was a postdoc at Caltech and he was a graduate student at Berkeley. And I think we spent some weeks observing at the telescope together. From 2014 to 2017, Chad was a Jansky Fellow of the National Radio Astronomy Observatory, and he spent this time at the CFA at the Center for Astrophysics at Harvard Smithsonian Institute, so in Cambridge. And in 2017, he moved to South America, to Chile, where he assumed the position of project assistant professor at the National Astronomy Observatory of Japan. And since then, he has been working on ALMA, so a bigger radio interferometer, and he has been developing a polarization system and commissioning the polarization system for ALMA. So as I have understood from the presentation, he's an expert in polarization, particularly millimeter wave. And today he's going to talk about star formation, polarization, and magnetic field in the ALMA era. So with that said, I'll pass the control to you. So start whenever you're ready.
Excellent. Thank you for the wonderful introduction, Andrea. It is an enormous pleasure and honor to be talking with you all today. Thank you so much for the invitation. As we've all lamented, I've talked to many of you today, which has been totally fantastic. It would be really great to be just having wine and cheese afterwards in person, you know, but alas, this year is just not going to let it happen. So in the future, we'll make it happen. But for now, we're stuck to our screens, and I hope to fill your screens with nice images that will tell you a variety of stories about this large title here, star formation, polarization, magnetic fields. And I'm going to tell you some of the, a lot of the background of why we should care about star formation. And then I'm going to zoom into some of the most recent work that my group has been doing to try and untangle how the magnetic field plays a role in a number of different scales. And I want to thank a lot of people. You know, my clicker's dying already. Oh, hang on a second. Sorry. Off to a great start. Okay. There we go. I want to thank a lot of people who've contributed to this, many of these projects that I'm going to tell you about today. In particular, my PhD student, Valentino Guelec, who's about to graduate, and he's on the job market, hint, hint. So he's done a lot of really great work. So I'll show you some stuff that he's done with me over the last couple of years, as well as one of his in-progress works toward the end of the talk. So big picture, how do stars form? This is the ultimate question. This is one of the biggest questions in astronomy. Where did we come from? What are our cosmic origins? And how did the universe and the galaxies within it evolve? All of these questions come into play when you start asking how stars formed. And I like to start on the galactic scale here, because within various parts of this galaxy, in particular the dark regions that you can see, those are the spiral arms of this galaxy, stars form. And those are these dark regions are giant molecular clouds. These are very, very large, gravitationally bound objects within disk galaxies like our own Milky Way that form stars on much, much smaller scales than what I'm showing you here. Now, the reason I'm showing you this slide first, I want you to focus in on the lower left on the scale bar, which I try to remember to include in all of my slides. This is a kiloparsec. So these giant molecular clouds are typically a few kiloparsecs in size. And yet, stars like our own sun are 1 solar radius in size. And so we're talking multi-spatial scales. The star formation is not a problem just on galactic scales or high redshift cosmic scales or local star forming region scales. It's a question that spans all scales from galaxies down to protoplanets. And so I just am trying to give you a gut feeling for the full set of more than 6 orders of magnitude in spatial scale that we have to move through in order to get stars formed. And so now I'm going to collapse this, and the only kind of animation that I could give you to kind of show you how we move from face on to in the plane of our Milky Way. So this is now from our perspective. So put yourself on Earth, where we all are, in front of all of our computers, and check out this image from Gaia. So this is a very, very nice image that's been making the rounds in the press lately from the Gaia satellite. And the dark regions that you see here are fundamentally the same as the dark regions from the previous galaxy. They're regions that are cold, dense, have a lot of dust and molecular gas, and regions in which stars form. Now, in the lower left, I put again the scale bar, but now instead of a kiloparsec, it's 50 parsecs. This is the typical size of a nearby star-forming region, many of which you can actually pick out in this image. And I can put a box around Orion, our favorite that is a winter constellation in the Northern Hemisphere and a hot summer one down where I am. And this is scaled, I say here, scaled to the distance of Orion because this image doesn't actually really have scale. What this image is when you look in the center, you're looking toward the center of the galaxy. Whereas when you look toward the edges of the image, you've wrapped around your head and you're looking behind your head toward the galactic anticenter. So you're really seeing everything. But the dense matter that we see that's forming stars here is biased in a sense toward the stuff that's closest to us. So you can actually pick out the Orion star forming region and a number of others that I'll show you later. And so we're talking smaller scales here. So we're several tens of parsecs. But stars form, for example, at the tip of this arrow in a size of a disk that is at most 0.001 parsecs, probably significantly less, especially if it's really young. So again, I'm just trying to give you a feel for how many orders of magnitude in spatial scale we're working with here. Now, one of the problems in star formation, one of the many big problems that people have been working on for decades, is despite the fact that there is a ton of molecular gas and dust in all of the galaxies like the Milky Way that could form stars, if it were to, say, free fall collapse under its own self-gravity, it doesn't really do that very efficiently. The star formation rate of the Milky Way is a meager 1 solar mass per year, whereas it should be a lot more. And then, for example, high redshift galaxies, there's many that are forming hundreds of solar masses per year. So why is it that normal galaxies like the Milky Way are forming so few stars? This is a kind of big, fraught question. And one of the prime suspects for the reason behind this low efficiency is something that is no stranger to this department, and that is the magnetic field. So you have here a view from Planck, and in my particular field, this is a very famous image. This is looking at the whole galaxy. You're looking at the same image, essentially, of the galactic plane and everything above and below it, projected around the back of your head toward the galactic anticenter. You're looking at everything, but now in polarized light from dust emission. And it's showing you that we live in a turbulent and highly magnetized galaxy. And it is thought, for good reasons and borne out in simulations and also some observations, that the magnetic field may be, I put it here in capital G and capital R, the great regulator. The magnetic field can have a lot of important dynamical impact on how stars form across all spatial scales, from galaxies, which is what you're seeing here in this Planck image, all the way down to the spatial scales that many of you all in this department work on now, at the scales of disks, even smaller at the scales where jets are launched, and all the way down to the scales where you have planetary magnetospheres interacting with their host star magnetic field. So the magnetic field is clearly important on all scales. And I apologize for this cartoon. This kind of erases the gut feeling ability for you to tell the difference in spatial scales, but it shows you a different cartoon view of how stars form. So now in the upper left, imagine that you're back in the spiral arm of that face-on galaxy. And then within that giant molecular cloud, you form a clump. A smaller piece of that could be a so-called protostellar core. That's a clump of gravitationally bound material inside of which maybe 1 or 2 stars might form. And around many of those stars you see here at the bottom, planet-forming disks form. And ultimately, after those evolve and the gas and dust are accreted onto planets or they're blown away by radiation, you ultimately create solar systems like our own. And this, again, as I put just in numbers here, is a very multi-scale process. And that's the perspective through which I want to tell you the stories I'm going to tell you today, with the connection, the common thread of the magnetic field. And now, usually people put the jokes like 2/3 of the way through the talk, but since everybody's probably been on hours of Zoom meetings already today, I'll just do a little bit of combating Zoom fatigue right now. So I saw this cartoon in AAS recently. This happens a lot to me, actually. So this person is giving a talk, maybe one of you, says, any questions? And then this is me in the second row. So have you considered magnetic fields? At which point I get thrown out of the window. Or I say, what about dust properties? Or what does that look like when you look in polarized light? All of these things make people want to throw you out a window. And it's because many people assume that magnetic fields are scary or difficult or complex. And yes, they are somewhat complex, but I want to tell you, my talk today is really trying to tell you that the magnetic field is not scary. The magnetic field and polarization observations are actually incredibly key and very, very useful for cracking open these really hard questions that we've been trying to answer, and that are now, the answers are now becoming accessible because of the incredible acceleration of technology in this field of polarization and magnetic fields over the last just 3 to 5 years. And that's what I really want to dig into during today's talk. So now the overview, just a few bullet points. I will begin by introducing my slightly more detailed view of magnetized star formation. And then again, through the lens of multi-scale, so you can kind of keep a logical flow in your mind of what we're talking about, I'm going to start on cloud scales and then go down to star forming scales and talk about the importance of magnetic fields and also what they look like, what the structures are, and how they may be playing a role in the formation of stars across these scales. I'll tell you a few stories about some papers that we've written in the last few years about a potential case where a star formed in a weakly magnetized environment, and then the very, very recent stuff about how we see some really interesting and highly unexpected features, including outflow cavity walls that are highly polarized, and these other structures that we think may actually be magnetized accretion flows. And then the final bit of the talk, I'm going to talk about disks. Typically, what we see is polarization from scattering, but there are a number of mysteries that remain to be solved there. And then I will conclude. Now, I should have said this at the beginning. Feel free to belt out your questions at any point. This is what I would prefer in person. I know it's a little more difficult over Zoom, and I'll stop at the end of each subsection to see if there are any questions, but please feel free to ask questions as we go. It's totally fine. And I don't want to lose anybody. I want to make sure that everybody's on track with me here. Okay, so let's zoom back out, and I'll show you an optical image. This is a star-forming cloud. It is a quite famous one. It is the Musca-Dart cloud. It's a little bit hard to see in the lower left because it's an absorption. So this is, note the scale bar, about 10 parsecs. So this is, say, a piece of the molecular cloud based on the little box that I put around Orion in the Gaia slide. So that's the physical scale that we're on. And now you zoom in the upper right, and you see these black line segments. What those are the inferred magnetic field in the outskirts of this region. And the fact that the magnetic field at these scales is perpendicular, more or less, to the spine of that cloud all the way down its length suggests that the magnetic field is actually dynamically important in guiding the material that ultimately forms that structure. And the reason I say that is because the magnetic field in the interstellar medium is what we call flux frozen. It's basically stuck to the material in the ISM such that it's much easier for material to flow along the field lines like beads on a string than it is for the material to pull perpendicular to the field lines because they experience a tension. So that was the kind of paradigm from large scale observations like this. Now what you're seeing here in cartoon form, now zooming to the microphysics, is dust polarization. So what I show you here is a little cartoon that I drew about how dust grains can absorb background starlight and show you the inferred magnetic field. So here on the right, you have an unpolarized background star. In the middle, you have my cartoon population of dust grains. In the interstellar medium, like what I just showed you, they're about 1/10 of a micron in size. They're spinning, and they tend to line up with their long axes perpendicular to the magnetic field, which I draw as these straight lines here in the middle of the slide. This is via a phenomenon known as radiative torques. I just put here rats, and the B hyphen just means that it's radiative torques that line dust grains up with respect to the magnetic field, hence the B rats. And then in the case of absorption, you see the polarization along the inferred direction of the field. So what I do typically is not actually background starlight absorption. Rather, I do polarized dust emission in regions that are very, very dense and you can't actually see behind them. They're too optically thick. In that case, you're looking at the same population of dust grains, but instead you're looking at the polarization from their emission. So they emit polarized light along the long axes of the grains. And then to infer the magnetic field, you simply take those line segments and you rotate them by 90 degrees. That's par for the course in this field. And when you look at the same source and you overlay the data from, for example, Planck. So here, again, this is background starlight absorption in the optical. Now I'm overlaying 850 micron Planck data. The Planck is the large single dish satellite that made that beautiful magnetic field image at the beginning. And then you can look at the polarization. So Planck had the ability to look at polarized light from dust, and you see the exact same orientation of the magnetic field. And there have been papers on this comparing background starlight and polarized dust emission, and it's the same. It's the same population showing you the same inferred magnetic field. So what was found on large scales? Again, I show you the whole galaxy. Now we don't just see Orion on the right, but we see many other star-forming regions, and they did a lot of statistical analyses, the Planck team, that is, after the 2016 data, the data came out in 2014 or 2015. And they came to the following conclusions when they were analyzing the structure of these star-forming regions alongside the beautiful polarization observations that came with them. And to boil it down to two sentences, what they found was that magnetic fields in dense gas, that is the gas out of which stars are going to form, typically filamentary structures, tend to be perpendicular to the magnetic field, which goes in line with essentially what I've said so far, that you have a relatively strong magnetic field at these large scales and you're collapsing along the field lines to form these large scale star forming structures. So where I came in, which is I was very lucky to get in on the ground floor of this field back when I was, as Andrea said, I was building and installing and calibrating the polarization system at ALMA. The question we could start to ask in survey mode was, what's happening at small scales? And by small, I mean less than 1,000 AU, less than about 10 times the diameter of our solar system. And this is, again, a question that many of you all in this department ask. It's something that is important on the scales of jets. Winds that are launched from disk surfaces are launched because of magnetic fields. Protostellar surface magnetic fields at even smaller scales are mapped by these beautiful observations from Zeeman Doppler imaging, and you get the importance of magnetic fields at even tinier scales between the surfaces of stars and the planets near them. Yes, David Alexander has raised his hand. Please ask a question.
Yeah, thanks, Chad. Just before you go on, when you say that the field is kind of strong, you get strong magnetic fields, is that relative magnitude compared to other regions, or is it relative to the gas? You know, the plasma beta, for example, in these systems.
Yeah, that's an excellent
when
question.
you say it's large, can you just sort of distinguish what the comparison is?
Indeed, and I should always say that. I apologize. It's always relative to something else. And I'm going to talk more about that actually when I show some simulations in a few slides. When I say strong magnetic fields, I usually mean relative to turbulence. So in a turbulent molecular cloud, for example, if you have very, very strong turbulence, then you can just totally tangle up the magnetic field and get nothing as well ordered as that. But when you compare, for example, with gravity, we know that gravity always wins. Right, the stars form, and so at some point the gravity's winning, and you're collapsing, you're forming your star. So it's the question of strong relative to what is really size scale dependent. But what I mean is on the scales probed by Planck, which are typically tens of parsecs or so, the magnetic field played a guiding role in forming the dense structures. So it was strong enough to not get completely tangled up by the turbulent gravitational collapse of those structures. That's essentially what I meant in that previous slide. But the answer to that question is different depending on what scales and what kind of physical parameters you're looking at. All right, excellent.
Chad,
So,
and maybe, sorry,
yes,
the question is
please.
about the scales. For somebody who's not an expert in astrophysics, what is it in absolute units? So the kind of fields that you're talking about, could you compare it to the Earth's magnetic field? Is it orders of magnitude more?
Yes, it is. So the basically working from the small scales up in these the cartoon on the right of the say T Tauri star magnetic field, for example, and then of the actual data in BP tau here, those can be of order kilogauss. So those can be several kilogauss, I think up to more than 5 kilogauss. In strongly magnetized so-called protostellar cores, these 1/10 of a parsec, several thousand AU size objects that I'm going to show you many of in the coming slides. At most, from our methods of estimating magnetic field strengths, they can be about 1 milligauss. And then in the interstellar medium on the scales, for example, outside of that spiny filament of the star-forming cloud that I showed you in the optical absorption image, they're about 6 microgauss. So that's a typical number for the ISM. So very, very many orders of magnitude different. On the scales that I look at with ALMA, it's usually hundreds of microgauss or 1 milligauss, more or less. But that's generally the range where we are.
Excellent, thanks.
Yeah. So the question, this used to be a slide that I would use only at one scale, but it's turning out to be a very much multi-scale question. What is the role of the magnetic field in star formation? And that's really what guides my projects, which now are on all kinds of different spatial scales. Is it fundamental? Is it the iron endoskeleton of the interstellar medium and star-forming cores? Or is it like the smiley face on the cup of cappuccino in the fancy downtown Houston cafe that is so difficult for the barista to make and they overcharge you for it, and then you stir it once and it's just gone, right? So that's really the question. And we are now addressing this on multiple different spatial scales, from clouds all the way down to disks. And if you would like more details on this, I just want to show this citation that I led a review paper on this with my colleague Qizhe Zhang at Harvard, looking at all of the interferometric polarization observations, that is, observations of magnetic fields with interferometers like BIMA, the SMA, and KARMA, and all the way up through the very beginning of the ALMA era. In 2019, we discussed a number of questions in the field, and really it's a lead up into the now exploding field of interferometric star formation, which is going to just continue exploding as we actually have additional not only high resolution instruments in the future, but additional instruments going back all the way up to cloud scales, looking at magnetic fields with just unprecedented sensitivity. So allow me to continue introducing magnetic fields and star formation, but at a slightly smaller scale. And I want to do this through the lens of quote unquote strong field star formation. And again, this kind of, David could ask the question again, what do you mean by strong field? And I'll sort of explain this as we go along. But this is the paradigm that a lot of people assumed stars would form under. Okay, so there are two key things that you expect to see if you are forming an individual star or a few stars in a strong field situation. And one of them is a consistent orientation of the magnetic field across scales. So this busy plot from Hua-Bai Li in 2009 shows you two different scales. So in the background, in the dark red, you can see this very large bar that the huge arrow is pointing to. That's the average magnetic field orientation, again, from background starlight polarization at 100 parsec scales. And then the insets, you see the little tiny insets that say D, E, F, G, H, and then you have the blow-ups here in the color scales. Those are protostellar cores. Those are 1/10 of a parsec sources that are forming 1 or 2 or 3 stars. And the white bars are the orientation of the magnetic field in those sources. And in a different plot in this paper, he showed that there's a very, very good correlation across now 3 orders of magnitude at spatial scale, which suggests that in this case, so gravity's winning, you're collapsing to form stars, but the magnetic field is regulated. This is magnetically regulated collapse to form stars. So that's one hallmark of strong field star formation. The other one, when you get down to the scales that are only accessible by interferometers like ALMA and KARMA and SMA, you get an hourglass. This is this pinch. So this is a model of an hourglass where if you have a strong field, it's probably not going to be wrapped up or tangled up too much. So you say it's poloidal, but then you have a star forming in the middle, and near that gravitational potential well, you're going to pinch the magnetic field. And then when you project it onto the plane of the sky, because all the images that we get in dust polarization are essentially 2D pictures of the magnetic field on the plane of the sky, you're going to see this hourglass pinch. And this actually has been seen a number of times. I'm just going to show you a better cartoon to illustrate the kind of structures that we're looking at here. This is from the inimitable Bill Saxton at the NRAO, who makes many, many beautiful cartoons. So in the very center here, you can see a protostar, which several of you all in the department study. And then around it, there's the disk, maybe 50 or 100 AU. Again, also something that is well studied at Rice. And then we have outflows blasting out from either the disk and or the surface of the star. They're removing material, they're removing angular momentum. And most importantly for this talk, you have these little blue lines that pinch in this theorized hourglass and go back out. Those are the magnetic fields. So that's kind of the situation for a lot of the sources that I'm going to show you. So here are observations. These are two sources. On the left, it's two different observations of the same source, a very famous low mass star forming core. The color scales in all of these and the contours in the upper left, that's the total intensity Stokes eye dust emission. So this is thermal dust emission. And all of the line segments that you're going to see up toward the end of the talk, those are all inferred magnetic fields from dust polarization. And you can see this beautiful pinch in these magnetic field orientations, both on the left and in this other source, L1157 on the right. The contours here, by the way, and I'll show you a few more of this kind of thing, those are the outflows. Those are the red shifted and blue shifted lobes of the bipolar outflows that are removing material, usually seen in CO, in CO emission. So the question was, is this always true? So we've seen some cases where the magnetic field is really holding on to the star formation. You have consistent orientations. You frequently see this hourglass. Are magnetic fields really guiding star formation all the way down to the scales accessible to ALMA all the time? That's really the question we wanted to know. And so we turned to ALMA and we looked at a bunch of sources, following up on a big survey that I did with Karma in graduate school. And we found one particular case that I want to show you about that was clearly not a case of strong field. So this is what I label weak field star formation. And the answer, again, in this case, is going to be weak relative to turbulence, not relative to gravity, because gravity is going to form the star. And this is the unceremoniously named Serpens Embedded 8. Allow me to show you the ALMA data in full screen. So again, the background grayscale is thermal dust emission. The white line segments are the inferred magnetic field. And what you see here is essentially a mess. Now, the scale bar on the right, if you actually squeeze it down, the inner black part of this grayscale is essentially, it's bigger than the size of a circumstellar disk. So what you're seeing here, imagine putting the solar system basically under the inner line segment in that plot. So you're seeing the chunk of semi-spherical material that is ultimately going to form the disk at the center, but this is kind of the natal envelope around the star. And the magnetic field is totally tangled. Yes, David, one more question.
Sorry to interrupt, Chad, but when you're looking at this, when you're measuring the field lines that you're showing here, is that all the field in the system, or is that observation limited so that you're picking out, you know, a certain polarization signal? Or when you don't see field lines in this picture, does that mean there's no field, or you just can't measure it?
Yeah, that's a very good question that in fact couldn't really be answered by previous interferometers, but with ALMA, we're starting to get a feel for the answer to that. So what's the clearest way for me to answer this? The answer is there's almost certainly field everywhere, so that's one thing. But the fact that you can see a lot of Stokes eye, so a lot of grayscale, where you don't see any line segments, actually tells you something, and this is something that's been studied a lot also at single dish Planck scales of clouds. It tells you something about some combination of the efficiency of grain alignment with respect to the magnetic field, as well as the possible integration of tangled magnetic field along the line of sight, and more basically just the orientation of the magnetic field with respect to your line of sight. So if you have aligned dust grains, you're going to see a much stronger polarization if you have a magnetic field purely in the plane of the sky. So that's something that I didn't emphasize enough at the beginning. When you see a line segment, you're only inferring the magnetic field in the plane of the sky. Okay, so those of you who work on Zeeman, for example, that's probing purely the line of sight. So this is a different mechanism that's only getting the plane of the sky. And in this particular case, you're getting the plane of the sky integrated and averaged through the entire volume of this optically thin object. So there's a lot of averaging going on here, and you're only probing one component. But it is indeed interesting and a good way to study grain alignment efficiency, essentially, to look at where you see signal and where you don't. And if you're not limited by signal to noise, which in a lot of these pixels, we're not limited by signal to noise. In some cases, we see very strong Stokes eye and no magnetic field. And in other cases, you see, like up here in this, the filament in this upper region here, you actually see relatively weak Stokes eye, but booming polarized signal. And so you can actually derive a lot of information from that. So that's a poignant question. So with these data, we can, of course, do the beautiful interpolation a la Van Gogh, the way that we did in the Planck map at the beginning. This is thanks to my co-author, Phil Motes. And then you can just go all the way to the press release and show the NRAO image experts' vision of a turbulent magnetized star-forming region. That was really the focus of our paper, that what we're seeing here is not strongly magnetically regulated. And to go back to the data, this is a multi-scale study. This was the first attempt to kind of get a feel for what's going on across a few orders of magnitude and spatial scale. So in the bottom right, you can see the data that I just showed you. In the center is the data from KARMA, so that's lower resolution, lower sensitivity observations from a previous generation telescope. And on the left is even older, even less sensitive observations from a single dish telescope, the JCMT, with their first generation polarimeter. But nonetheless, with those data, we did a comparison of the orientation of the magnetic field as a function of scale, and then did a statistical comparison to determine what state of star formation this object formed out of. But we wanted to be a little bit more quantitative, and so yes, Chris. I like this hand raising.
Your cartoon, your fancy cartoon there, was down at the stellar scale.
Indeed.
So for this source, I'm not that familiar with it. Is there an optically visible T-Tauri star that we can see accreting there, or is this licensed?
I now realize that I have confused you with the press release image. I apologize. There is no optical source that we can see in there. And indeed, you have a very good point that this actually looks more like T-Tauri fields interacting with the inner disk at 5 AU than it does actually a protostellar core. The idea was these clouds around the outside are the core of natal material out of which the source is forming. But no, there's no optically visible source here. It's very, very embedded. Yeah, these so-called class 0 sources, that's the term of art that we use, they typically are invisible in the near infrared and the optical. Occasionally you can see something if you have the orientation about right, if you can see emission coming out of the outflow cavity, for example. But typically they're at very, very high AV, high extinction. Yeah, sorry about that. So we wanted to be more quantitative in our analysis of this tangled object. And so we compared with AREPO simulations. AREPO is a cutting edge MHD that is magnetohydrodynamic code that has the ability to get extremely high dynamic range in terms of spatial scales. And so this is run by my colleagues who were all at Harvard during the time that I was there. Keep an eye on the magnetic field strength up here, that's in microgauss. I'm just going to show you 2 cases out of the 4 that we ran, one of which is very, very weak field, again, relative to turbulence, and the other one is very strong. So the first case is here, the box scale on the left, which is essentially larger than the single dish scales. The JCMT is one of the single dish instruments that had the largest scale observations I showed you in the previous slide, excuse me. That's a chunk of a molecular cloud, it's a few parsecs. And then you zoom through the intermediate scales down to the scales probed by ALMA, and you don't see anything in particular. You just see that it's a mess on every scale. You don't see any consistency in magnetic field, and you basically just see that turbulence and infall are dominating the structure. However, when you pump, yeah.
Quick question.
Yeah.
So for the bottom right one, would you actually expect to detect that, all that polarization, or would some of these be undetectable even with ALMA?
Yeah, a lot of that would be undetectable, and the reason is, that's a very good question. So if we had the ability to look at all spatial scales with that kind of resolution, then we could potentially make a map like that. But ALMA typically filters out large scale structure, and so a lot of the very, very smooth material that you see around that little dense blob in the center would ultimately be filtered out by the interferometer. That's why we're able to make these kind of these maps with very nice sharp features, and then outside of it, you don't see anything else. So it would be not particularly likely that we'd be able to see with that kind of resolution the outer material, but seeing the material that's outside of that inner little bit is indeed part of the story of multi-scale star formation, and we can access that with current single dish telescopes that don't filter nearly as heavily, and also future telescopes that are going to have quite good resolution with much higher sensitivity. So that's a good question.
Thanks.
Yeah. So here's the other case. This is the strong field case. So again, the grayscale, sorry, I neglected to say the grayscale is the same on the top and the bottom. The bottom, you see the magnetic field. Now you see both of those hallmarks that I mentioned before. You see beautiful consistency of the original east-west orientation of the magnetic field. If you look carefully, you can see a little bit of pinching here in the bottom right, in this hourglass form down where you get to the ALMA resolution. And then in the upper left, you can actually see a number of other things that we very typically see in magnetized clouds. You can see the magnetic field along these non-gravitationally bound striations of material, and you can see dense, darker, gravitationally bound filaments that are perpendicular to the magnetic field. This is sort of similar to some of the stuff I mentioned at the very beginning in the Planck maps. So to wrap up the story, a statistical comparison of the data and those variety of simulations that we ran showed that, at least in this case, a source is forming not in a strongly magnetized environment, which is reasonable. I think that it's as we keep looking at sources like this and we get a better sample, we're really going to see that everything falls on a continuum. There are a small number of sources that really show strongly magnetized star formation, but there are some others where infall and turbulence are really taking over at the small scales. And one of the big questions that we have, which I'll touch on at the very end, is where does this transition happen? Why is it that the magnetic field maintains its integrity down to smaller scales in some sources, but not others? Because gravity does always win, but at what spatial scale does it win? And why is it different in different sources? So that's one of the main things that we want to go after in the future. Okay, more questions on that before I switch gears? Good questions so far. I like this. Okay, so let us continue. So this is more recent work. As we continue doing single source studies with ALMA, as the mode only opened a few years ago, where we were able to do these incredible maps of magnetic fields and polarization in this type of source, we started seeing some trends. And the first very clear trend that came out was outflow cavity walls that have strongly enhanced dust polarization. And so one of the first examples I'll show you here is B335. This is another class 0, very young embedded protostellar source. And you're seeing the same type of observation here as the ones I showed you before. The line segments are the inferred magnetic field. I'm only showing you the outflow in arrows at this, in this particular slide, but you can clearly see that if in your mind you have this outflow going this way, and in other sources I'll show it more clearly, at the edges are the edges of this cavity, and you see very, very strong polarization and magnetic fields that are well aligned with the edges of this structure. And just a note, for the next subsection, there is also very strong polarization in regions that are not associated with the outflow cavities, which I'll get to in the next chunk of the talk. We kept looking at other sources and we kept seeing similar things. So here's yet another source, BHR71 IRS2. Now I'm going to show you the outflow in all of its blue and red shifted glory. And again, the line segments are the magnetic field. In this particular case, we started to dip our toe into the world of astrochemistry. So now you see that this polarized emission here is actually sandwiched between the outflow lobe here. So this is the red shifted outflow lobe in CO. Here's the strongly polarized dust emission. And then you get this unpolarized, cold, kind of a filamentary bit of N2D plus emission. N2D plus basically traces cold pre-star forming material. And the lack of polarization everywhere except the cavity walls, in addition to the fact that we had this strong filament of N2D plus, which had almost no polarization associated with it, started to make us think that maybe we're actually seeing strong irradiation of the outflow cavity walls that is somehow enhancing the polarization from aligned dust grains. So we kept looking. This is my student's paper from 2019. This is the partner of the weak field source that I showed you before. This is Serpens embedded 8 North. And again, this appears to be quite common. In the line segments, you see the magnetic field, and then you see this beautiful CO jet in blue and red. And we see, again, enhanced polarization along the outflow cavity walls. But in this case, we had a different tracer to give us an idea of the astrochemistry. This is CCH. So CCH is a known tracer of UV irradiation. And so what we're beginning to think now, okay, so since this is UV irradiation and these outflows actually evacuate a kind of semi-cone shaped bit out of these clouds, thus allowing high energy radiation to escape, maybe this really is what's going on. Maybe we're seeing irradiation of the outflow cavities. And actually, when we dug back in the literature, going back to the first source I showed you, we saw that this was also true here. So there's CCH now overlaid with the dust polarization in this first source. So this is really, it's clear that this is something to pursue if we want to understand the physical properties of what's going on deep inside these protostellar cores. And here's a cartoon showing you more or less what we think is probably going on. You can see a jet and an outflow in this long straight thing. There are shocks along that structure that could also be producing high energy radiation in addition to the UV photons and X-rays that are coming out of the accretion onto the tiny little central source here, which are able to propagate through that evacuated outflow cavity and impinge on the cavity wall. So chemistry in outflow cavities is not something new. So this actually had been seen long ago in Herschel data and other single dish telescopes, but never with this resolution that we were able to get from ALMA. But the thing that is now bothering us and that we're still working on is UV irradiation can't actually get into the cavity wall. And what we've seen in several of these observations is resolved layers of polarization. So we see 200 or 300 AU thick walls that have strong polarization, so very, very significant dust grain alignment in them, presumably from this irradiation phenomenon. But if the photons that can get in are only long wavelength, then we kind of have a problem. And the reason that we have this problem, I try to illustrate in this optical depth cartoon. So if you look on the right, that's my cartoon outflow cavity wall. It's at about 10 to the 4 dust density, or 10 to the 6 per cubic centimeter particle density, if you include the gas. It's very cold. And you can see that if you just do back of the envelope optical depth calculations, the only photons that get in are in the mid-infrared and the far infrared. And again, we're seeing resolved polarization to several hundred AU in depth. So what that means from a kind of physics and dust perspective is that if in fact these radiative torques are the main reason that we're seeing grain alignment polarization, then the photons have to be similar to the size of the grains that they're aligning. If the photons that are getting in are greater than 10 microns or so in size, maybe 100 microns, that means you need to have very significant grain growth. And that is totally unexpected, because typically we assume that grains grow to large sizes and then form planetesimals and then form planets only in disks. And so to have very significant grain growth, thousands of AU away from the central source, from the central disk and the central star, is not to be expected, shall we say. So this is something that we're working on right now. This is something that my student probably at this very moment is working on. So again, my PhD student, Valentin, these are MHD simulations on the right. What he's doing is an analysis, a joint analysis of radiative transfer processed simulations, which you can see on the right here. In this particular case, I chose a panel that shows you in the color scale the polarized intensity, because what I showed you in the previous plots was the strong polarization along the cavity walls. You can see this nice enhancement here along the cavity walls. Again, very preliminary, very preliminary. And he's also taking a lot of the archival data of magnetic fields and polarization toward this type of source with ALMA, and is comparing with existing observations of UV sensitive tracers like CCH and C3H2. So that's ongoing work to unravel these mysteries. And before I go on to the next bit, was anybody like to ask questions about the outflow cavity walls? If not, I will carry on. Yes,
Chat, I have a question about what you said about grain growth.
Yeah.
Do you have spectral index information of the continuum emission that you could use to test whether this grain are really large or not? Because the emission here should be optically thin at millimeter wave, right?
Yes. The answer is, I think beginning around now, we probably have the multi-wavelength observations. The thing is that these outflow cavities are typically weak. I mean, you can see them in incredibly deep observations, which we have in particular at 850 microns and maybe 1.3 millimeters. To get a good lever arm for the SED, for the spectral index fitting, you really need to go down to band 3. And I think in B335, so my colleague and the co-advisor of my student, Anel Mori in France, she has 3 millimeter observations that are super, super deep of B335. And I think maybe she can see the outflow cavities in there. So the answer is possibly. And I think that will, it'll be simpler to do that kind of estimate in cores than it will in disks. So we're gonna get to disks in a few minutes. There is literature at lower resolution, I think by Jesse Jorgensen and other people, who looked into this and saw hints of low spectral indices, not nu squared, it's not optically thick, but significantly lower than they expected in protostellar cores. So there have been hints of grain growth just from the spectral index side of things for probably a decade now, but they weren't really resolved. And so remains to be seen what kind of grain growth will be revealed by spectral index tests.
Okay, thank you.
Yeah.
And chat, can I ask, I mean, what role does the gas play in all of this? And do you have to worry about ionization and, how that's affected by, the magnetic field and so on? Or is the gas unimportant for what you're talking about here?
Oh no, the gas is very important. Yeah, that's another thing that I appreciate these questions making me realize things that I should clarify at the beginning. So we look at magnetic fields through the polarization of dust, but dust is only about 1% of the mass. However, the other 99% of the mass, I'm actually going to touch on this particular point in one of my future slides at the very end. Gas is 99%, but the dust and gas, in ways that we understand relatively well, but not perfectly, are coupled, because this material, while it is weakly ionized, it is ionized. And so since the material is ionized, the dust tends to be the charge carrier. It is coupled to the magnetic field, and because of the densities essentially, and the lack of very fast so-called ambipolar diffusion where the neutral material slips by the dust grains, it is essentially all coupled. And so you can kind of see these observations of dust as kind of a proxy for where the gas is as well, to a degree. So I want to talk about more long, skinny structures that are truly mysterious. And this is something that's very, very new, stuff that has only come up in the last year or two. And these are magnetized streamers that are not associated with outflow cavities. So I'm showing you here a wide binary protostellar system in polarized light. This is the one that I showed you before with the beautiful outflow. So allow me to push the resolution of these ALMA data so that one disappears because we can't get it anymore because of sensitivity. And its partner, IRS-1 on the left, has this very bright, long, skinny thing. And so what is this, I say? And I'll give you half-tone image of the outflow. And you can see that this particular structure is not lying perfectly along the outflow cavity. And there are many, many other structures like this in different young star-forming sources that are even clearly less associated with the outflow cavities. And I'm going to show you a gallery here. So here's IRS-1. Here's the source I showed you at the beginning, where the outflow is actually in this direction, but you have this kind of filamentary structure here perpendicular to it. There's B335 with its beautifully polarized outflow cavities, and then this north-south bit above it. And there are several other sources, including one published by my student here in 2019. And so I'll put these ovals around it. These are all of these filamentary structures that are not associated with outflows and yet are still highly polarized. And what we know about them is they're thin, they're straight, they have very well-ordered magnetic fields and very high polarization fractions, and they tend to be oriented toward the central source. The best idea that we had for them a couple of years ago was that they might be accretion streamers because they're pointing down toward the center of these sources, but we didn't really have much in the way of confirmation of that until recently, when a whole set of new observations just in the last 2 years started coming out. So these are, with the exception of the simulation in the upper right, which is just designed to compare with these, the three on the left are confirmed accretion streamers. So these things I know they all look different. I apologize for those who are not intimately familiar with this kind of observation. On the left, you have a disc-like structure in these little lines, and then a blue shifted and red shifted kind of tenuous filament that's falling in from outside of the source, basically connecting you to the natal protostellar envelope. Here, you look at the scale bar, this is now actually a disk size. So this is a circumbinary disk, and these beautiful filamentary structures are actually feeding the southern source right here. And then in the lower right, there's a protostar observed by ALMA in the middle, and then NOEMA interferometric observations of this HC3N filament that's falling in toward the central source. So now we're actually beginning to see these accretion streamers thanks to new instrumentation that has the sensitivity and the dynamic range to look at both tiny scales as well as the core scales and to see how they connect. So we don't actually know the magnetic fields in all of these regions, and we don't have good tracers of spectral lines in the ones that I showed you in the previous slide. But it seems like we probably have a case to say that we've begun to unveil how the material is actually being delivered onto these central sources. And my bet is that it's along streamers that are highly magnetized. So even if the magnetic field is not actually guiding the full star formation process, it may be essentially reorganized into these, for lack of a better word, flux tubes, along which material can slide and accrete onto the central source or maybe the disk nearby. So that's, I think, a very promising path forward with this kind of observation. All right, I'm going to totally switch gears. I'm getting toward the end of my time here, so I just want to tell you a little bit about the mysteries of disk polarization. All of us who do magnetic fields and protostellar cores were super excited when ALMA's polarization system came online, because we thought, finally, we can look at disks, we can get the magnetic field morphology in disks, and we can constrain all kinds of questions that we've had. What is the morphology? What is the poloidal to toroidal component? What is the strength? Can we confirm the importance of the poloidal field in jet launching? Can we speak to the importance of the magnetorotational instability, which allows material to move around in these disks? And so we looked, and we saw scattering. So this is a model of dust scattering in a inclined protoplanetary disk, kind of on its side, and then inclined into the page. And this is not magnetic fields. So most of what I'm going to show you until the very end of the talk is no longer magnetic fields. We're just purely looking at scattering from a disk. And what is in this model is not too complicated. Basically, scattering, it's strongly wavelength dependent. You can see different things at different wavelengths. This is unlike magnetically aligned dust grains, which don't really have much of a wavelength dependence. And the scattering here, it's not like the standard light bulb scattering where you have a nice cloud of gas around a central light bulb source and you just see this concentric circle thing. This is what we call self-scattering. It's basically just distributed scattering within a smoothish disk of material. And at any given point, you simply calculate the prominent radiation direction, and the polarization is perpendicular to that direction. So that's the process that's going on, that's producing the scattering that goes into these models. And when you go back here and you look at one of the first well-resolved high signal to noise observations of polarization in a disk with ALMA, which is HL tau, this is the very famous disk that has the beautiful rings that were revealed in, I think, 2015. You see exactly the same thing. You see the polarization primarily along the minor axis of this disk. You get polarization fractions that match the models really well. And you get a little bit of kind of curving or beveling in the outer edges of this polarization pattern. But it does not look anything like what we expected we would see from magnetic grain alignment. So it's almost certainly scattering, at least at these short wavelengths. I just want to highlight IM loop. This is a source that I worked on. It's kind of similar to HL tau in some ways. And we see the same thing, just to say that we see primarily polarization along the minor axis, similar polarization fraction, and a little bit of bending toward the outer edges of that profile. Now we modeled IM loop, and this is just one example of many fits of models to this type of data over the last few years, and it came to essentially the same conclusion that all the other studies came to. So on the left, you have this nice synthetic observation run by Haifeng Yang, and on the right, in the upper part, you see a fit to the polarization fraction. So the peak of the observations that I showed you in the previous slide are about 1%. But if you tweak the maximum grain size of the scattering population just a tiny bit, you completely change the polarization fraction that you actually see in the model. And so this strongly constrains the maximum grain size to be of order or slightly less than 100 microns. And to someone who works on the ISM, that seems big, right? So these grains have clearly grown if these models are correct, but it's not big enough. So we know that in disks, the grains have grown. This is from spectral energy distribution studies across multiple wavelengths, and ultimately from the fact that planets form, and planetesimals form, and asteroids form. We know that grains need to grow. So this mismatch between the maximum grain sizes that we infer in disks from these other methods and these new scattering models is a mystery that has yet to be resolved. Now, there are even more mysteries. So on the right, this is the Rosetta Stone of disk polarization. And yet, unfortunately, the Rosetta Stone is not actually helping us untangle anything because we don't know what it says. On the right, you have band 7. So that's the short wavelength where we think we kind of understand that it's scattering. But then on the left, you see something totally different. I label this KRADS, okay? But there should be a huge question mark next to this. I'm simply using this as a placeholder until we finally figure out what's going on, hopefully in the next couple of years. This mechanism is known as radiative alignment. This is the K is the vector of the radiation anisotropy, which in a disk is very simple. The anisotropy is simply radial. And the idea here is that you still have the radiative torques, the photons, that are spinning up these dust grains and aligning them with respect to something. But it's no longer with respect to the magnetic field, rather it's with respect to the radiation direction. So you just end up with grains that are aligned with their long axes perpendicular to the radiation direction in this disk. That's the thought for what might be happening here. Turns out that when you do very detailed models, it doesn't really fit the HL tau data. So this is really still up in the air. But again, I'm just going to leave this here as a potential mechanism for what may be going on and show you just a tiny gallery, a very small sample of the sources that have been observed. Again, most of what we see looks like this, scattering, short wavelengths. Here's DG tau, another very famous disk. We see the same kind of scattering profile along the minor axis, but we see a similar transition here when you go to longer wavelengths that is also seen in HL tau. So this is this kind of azimuthal profile that we don't really understand. And in some younger sources, these deeply embedded, not quite as evolved sources, this is one called IRS-63, you actually see both. You see in the kind of unresolved inner region, you see a scattering profile along the minor axis in addition to this azimuthal profile on the outside. And then you just go to complete madness when you look back at the same source. So I use this source as an example of accretion streamers, which indeed is true. That's in the upper right. These observations here in these 3 panels are observations of the same source at lower resolution by ALMA at multiple wavelengths. And the fact that Felipe Alves, who did this nice work, saw the same orientation of the polarization. Note, I'm showing you the polarization, not the magnetic field. He saw the same thing across all these wavelengths. That is a key indicator of magnetically aligned dust grains. It's almost certainly not scattering in this case. The polarization fraction was also much higher than is expected for scattering. So this is very clearly magnetically aligned dust grains, and yet this is the electric field polarization. But if you know that these things here are accretion streamers, which they are, then the magnetic field must be along. It must be strung along the accretion streamers the way that these look, essentially. And so the question is, in this case, is the magnetic field actually also tracing the electric field, which is 90 degrees off from what I told you at the very beginning of this story? So we're really getting into the weeds here, but this is a very exciting new area where maybe when you have large grains, you can actually get polarization that's along the magnetic field as opposed to perpendicular to it. So there's a lot of really cool work going on here. And I just want to show you in summary, the push and pull among all of these mechanisms that are creating polarization at the smallest scales that I'm doing work. And now let's zoom back up. The summary of the potential weak magnetic field case of Serpens 8, where you don't see an hourglass, you don't see preservation of the magnetic field across multiple spatial scales. And we do some comparisons with these awesome simulations that help us constrain the role of the magnetic field in the formation of this kind of source and how you can actually change the ultimate morphology at tiny scales by tweaking the relative importance of magnetic field and turbulence at large scales. And then the newest stuff, magnetic fields and outflow cavities, we're working toward a unified model of how this works that can tie together the total intensity observations, the magnetic field observations, and the astrochemical observations. So we see this enhanced polarization that is associated with UV tracing molecules. But then we have this grain growth issue, which we can, as Andrea pointed out, we can start to untangle this with high resolution spectral energy distribution studies. And then we have accretion streamers, which have, well, what we think in polarization are probably magnetized accretion streamers, because we've started to see these in both dust and spectral lines, clearly oriented toward the central source. And if this is in fact true, these really open a window into how material is delivered from the natal protostellar envelope down to near the disk. You know, how do you get chemically fresh material into your planet forming region? How does the entire envelope actually collapse onto the central source? Is it calm spherical collapse? Almost certainly not. So this is one of the new avenues that we're pursuing. And just my last few slides, I think I am going over time, for which I apologize. Looking to the future for just 4 slides, I want to direct this at late stage undergraduates and very early graduate students with some projects that I have in mind and where I envision the field going over the next few years. So here, starting on the largest scales, magnetic fields from clouds to disks. This on the right, I showed you these plots from my work in 2017, where we really just started this multi-scale search. At the scale I put in the circle here, these data are already being improved upon, and the future is really at these scales and beyond. There are many, many new telescopes, including exciting ones like the Large Millimeter Telescope in Mexico, the balloon-borne polarimeter on BLAST TNG, which is the next generation of balloon-borne polarimeters following up on BLAST pol. Observations at multiple scales from these kinds of telescopes are going to allow us to ask major questions, not only what role does the magnetic field play on all these scales, but when does gravity finally win, as I discussed before, and why is it at different scales in different sources? Now, high mass star formation, this is something I didn't talk about at all. Feel free to ask me more in the question session. What I'm showing you on the top, on the right, is a quote unquote typical observation of the magnetic fields in a high mass star forming region. This is work by my colleague here at ALMA, Pablo Cortés. This is dust polarization, just like many of the other slides that I showed you, but the zoom in on the bottom is dust overlaid with polarization from CS. So this is spectral line polarization. This also tells you about the magnetic field, but getting back to David's question, what about the gas, right? It's 99% of the mass. These observations can tell you about the gas, and even more important, if you look at observations of polarization of spectral lines that trace different densities, which we have in this incredible data set of the survey of more than 20 of the brightest high mass star forming regions with ALMA, there's a lot of polarized line emission, and the lines trace different regions, some rarefied outer regions, some denser inner regions. We can actually try to start doing what people have been talking about for years, which is to do 3D tomography of the magnetic field, where you actually get an idea of the 3-dimensional structure, not only via velocity space, because these lines are polarized in each channel. I'm only showing you one channel of this data and velocity, but also via different spectral lines. So I think this is actually a really, really new, promising field that has been opened up by ALMA. Again, back to the delivery of material onto central sources. I talked a lot about this during the talk. We have a ton of data on this scale, which we've just started working on the last couple of weeks, actually. There's a first look image here in the bottom right. This is magnetic field observations with ALMA toward Orion, and we have a couple of other surveys in the works at higher resolution. So we can address the accretion streamer question and a totally different but equally important one, how do binaries form? So this source on the top, this is a proto-binary. There's a circumbinary disk around it. Half of the field star, or half of the stars in our galaxy are in binaries, but we know that the magnetic field should play a role in the formation of these binary sources, which tend to be, some of them are tight binaries at 100 AU scales, some of them are wide at 1000 AU scales. So finally, we have that magnetic field piece, in addition to data from other telescopes that show us the binarity of this entire sample of sources. So this is a really exciting path forward as well. And then back to disks, so going down to the smallest scales again, here's this totally mysterious Rosetta Stone of HL tau at the different frequencies. We're able to to get not only information about dust from polarization observations. I talked a lot about fitting dust grain sizes and the mismatches between the observations from other methods, but also we're working on being able to tease out also the magnetic field in these disks. The upper left image at 3 millimeters, that may be a magnetic field. We're pursuing this via other measurements as well, like spectral line polarization. And so this is something that is really, I think, going to take off in the future once we find out the way to dig out the magnetic field, because as I mentioned at the very beginning of this talk, the magnetic field is acting on all scales, all the way down to the scales relevant to the formation of substructure and disks, like the one I show you in the bottom right, and the ultimate formation of protoplanets, like this little one, PDS-70C, from Andrea's paper in 2019. And with that, I will finish. So thank you very much for your attention, and I'm happy to take as many questions as you're willing to give me.
Thank you very much, Chad. I'll applaud for everybody. So we are already well within in our virtual wine and cheese session. So if we're a bit late here, but no, if there are questions, we can smoothly fade into our informal gathering for wine and cheese. So if people have to leave, please leave. Otherwise, please ask questions.